Time to go to work. Lecture number 3, which should conclude our high-speed...
Hey, yo, come on, guys.
Lecture number 3, which should conclude our high-speed lectures. And then we go on to other things, slower things. I don't remember what I said.
Hey, you said something about emitter followers
There
oscillating.
were several people here who wanted handouts on why emitter followers oscillate. And it's not that you're being ignored, you were forgotten. I Xeroxed them all, put them on my desk. They sat all week and they're still sitting there. So it's the proverbial next time. But I found the good one, the really good one. The HP reference I haven't been able to find yet, but you'll get, at a minimum, you'll get one. And then you'll know why emitter followers oscillate in English.
There we go.
It should be kind of a crummy video. It's kind of like a hand-drawn schematic. It's worth more. You know, it's more realistic.
I should shake the camera or something.
I'd like a gate flash.
This is where we left off last time, and this you can see the figure numbers have changed from numbers to letters. And as is my habit, I do all my appendices with prefixed in letters.
What happened to the telephone sign, by the way?
Pardon?
You're not showing the telephone anymore.
Well, the telephones are gone because, in theory, these are not problems. These are supposed to be circuits that work. Okay, but we do get phone calls on them when they don't. But anyway, throughout the previous 2 lectures, I've made comments about scope overdrive. And now we're going to get down to the meat of the matter, which is, okay, Williams, you've been pissing and moaning about scope overdrive. Now, how do you really deal with the issue in resistor values and transistors? And this measurement problem, which is kind of a classic measurement problem, sets the stage for how to deal with the scope overdrive issue, at least in my opinion. One of the most difficult measurements to make is the settling time measurement, which is to say, you hit an amplifier with a hard, fast, clean step, and you want to know how soon it settles within some specified error band and remains there. So it's got a slew and ring about the final settling point and finally stay down. And the problem with that, of course, is the amplifier typically will slew volts. The standard test has always been 10, and then settle down within a millivolt or less. And the name of the game is, how in the name of God do you observe that settling time? Because you're asking the instrumentation to settle out to very, very small fractions, the total step. And the classic measurement situation where that's important is D to A converter settling. And the classic DAC arrangement is you have some nominally fast DAC, in this case a 12-bit kind of thing we're going to use, which implies we want to measure settling to 0.01%, which is a half LSB at 12 bits more or less. You unload a fast DAC into some fast amplifier, and this is the circuit you see on lots of manufacturers' data sheets, and if this is the way they measure settling time, then don't believe their numbers. Why? The reason is this. The way the scheme is supposed to work is you bang all the bits at once, you unload the current output of the fast DAC into the amplifier under test. This steps nominally the opposite in polarity of the point where you expect the voltage to settle. So this is going to go positive, and when things settle, that point nominally is at 0. During the time they're not settled, during the time this is slewing, this point is nominally bounded by the diodes. So what the scope sees is about a 600 millivolt overdrive. The problem is the scope's sitting at 2 millivolts per division, because I want to see the null within a millivolt or so. And there are basically no scopes that I'm aware of, with one exception, one class exception that we'll get into in a minute, that you can hit with a 600 millivolt, or if you go to Schottky, even 300 or 400 millivolts overdrive, and will recover within 2 millivolts and display anything meaningful on the screen within the kind of settling times people want here, which are typically tens to hundreds of nanoseconds. So how do you deal with this issue? No, I'm not trying to obfuscate the answer here. It's a terrible slide. It makes a much better schematic in a book, but it's not as bad as it looks if you really start to take it apart. For instance, this circuit up here is the one I just got through saying I don't like. Okay, what is all this junk down here? The way this thing is going to work is as follows. The way this scheme allegedly works is it clips the waveform in amplitude down to diode drops to prevent from overdriving the scope. And I'm saying that's not good enough. Suppose we did the following. Suppose we add a switch here, and at the time we tell the pulse generator to drive the DAC, we open the switch. So now the scope sees nothing. We're clipping the waveform not only in amplitude, but as far as the scope's concerned, we're clipping it in time. You tell the DAC to go, you open the switch, the scope sees nothing. We're going to sample. You wait until some length of time when you think you're well inside the clamp provided by these diodes, then you close the switch. So now they're going to see a very limited overdrive. So the name of the game is knowing approximately when this thing is going to settle. And the way this scheme works is, here's the basic circuit up there. I've gone to Schottky for a little better clamping. Now I've just got a fast open loop buffer. This comes over to here. Look at this bridge here. That is a sampling bridge. What we've reproduced here is the front end of an old-fashioned 1960s era, what I call true no-fooling sampling scope. This bridge here is controlled by all this junk down here. It's basically a switching bridge such that when this signal is sitting here, that's what we want to switch. When these sides of the bridges are exercised by all this switch biasing circuits in here, this signal appears over here. That's the output of the measurement, basically. And how do I do the switching? The way this thing works is, and not focus this slide. The way this thing works, at the same time that you bang the D to A, you hit this one shot. So you generate a delay, and you open up the sampling bridge. So all the slewing and horrible stuff that's going on over here sits on this side of the bridge, doesn't appear there. After some adjustable delay time, so you're basically going to peel back the time in negative fashion, you're going to catch the trailing edge of the settling right there. You're going to let the bridge close. Okay, so you clip the waveform in amplitude and in time. Why do I use a bridge? Why don't I just use a FET switch here? Why do I go through all this bridge business? The reason is the gate-to-source capacitance in a FET will generate more waveform artifact here as I drive the gate. No matter how careful I am about the gate drive, you've got capacitance from gate to channel, and you're going to dump charge onto this line, which is probably going to be a larger amplitude signal than what you're trying to see. So you'll probably end up overdriving the scope anyway. The magic of a sampling bridge like this is the approach is fully differential. You remember the sample and hold we had back, I think, in the first lecture, where I used a bridge like this for the same purpose. I was using a 10-puff sample hold capacitor, and I couldn't afford any charge getting through the switch. There's no way I could use a FET. Same approach here. The bridge is fully balanced to the extent that my layout and my timing skew and my drive to the bridge are absolutely matched. There's going to be nothing come out of this thing. The price you always pay for a sampling bridge is you're relying on the DC matching of the diodes. So what you get in a sampling bridge is you get very, very good AC switching performance with regards to parasitic charge ending up as waveform artifacts out here. What you give is it's hard to make a good one at DC. So what do we get? Okay, you build all this junk up, you go through all this stuff to get this picture. The guy on top is the input pulse. That's telling the DAC and the one-shot to go to work. So during this interval here, the waveform is slewing 10 volts. It's going right through the roof, and you can see the bridge rejects just about everything. There's a few millivolts of stuff in here leaking through as the bridge is moving volts at speed. Now the one-shot times out, the switching bridge comes on, and you catch just the last 20 millivolts excursion or so. That's it. The scope never sees any off-screen activity at all. Okay, and you can see what the measurement here indicates is 1, 2, about 280 nanoseconds to about a millivolt settling on a 10-volt step. You'll notice something else here. There's a port here, it's hard to read, but there's another output here indicated. It says output to sampling oscilloscope. What that means is if I've got an old-fashioned 1960s era no fooling sampling scope, this circuitry's already there, so I don't have to build that. If I've got one of those, I can just, like an old Tech 661 or a Tektronix 1S1 plug-in for 500 series stuff, I can just hang it right there, and I'm not going to have to do that. I'll just trigger the scope off the one shot. This measurement's very important to people who sell and use D to A converters, and the number we were after was 300 nanoseconds. So at this point, all the marketing guys jump up and down and say, great, we've verified 280 nanoseconds. Let's sell the thing. I wasn't so happy about that. I wanted to run the test a couple other ways and get agreement, because all you ever think about as an engineer is the 747 coming in to Kennedy on a winter night, and is it really 280 nanoseconds or not? Here's another way to measure settling. I basically went and got a sampling scope. So I basically replaced my homebrew sampling stage with a no fooling sampling scope. In this case, a 1S1 plug-in. And that plug-in is a single trace kind of thing, but take it for granted and believe me that the events initiate here. And this feels real good. It's 100, 200, 280 nanoseconds to about 0.01%. See all the dots and stuff? That's the way a sampling scope looks, because that's what you're doing. You're literally taking pictures. That's why the display looks so granular. So that feels pretty good. I've essentially measured this with a similar method, but with two different rear ends, and I get agreement. Finally, there was a guy back in the 70s, actually the 80s, a guy by the name of Barry Harvey, who published a method which was similar, okay, same kind of thing. He clips the measurement in time. What I consider to be a much more complex method, but I went ahead and built it anyway and measured it with that method and got 100, 200, about 300 nanoseconds. But if you study Barry's paper very carefully, the way the thing works, you get to subtract 30 nanoseconds. So you go, yeah, that's pretty good. That's about 270. Fine, we can build this product and ship it and spec it at 280 nanoseconds. But the core of what I'm trying to tell you here is that when you make these measurements that require fantastic off-screen overdrives, and in fact, when you make measurements that require any off-screen overdrive, whatever, you have to exercise the greatest degree of caution. And the ultimate degree of caution is you just don't let the measurement go off-screen. Let's see, this is... Okay, one more thing about DACs, of course. You'll recall in the original circuit here, I indicate a feedback capacitor. All DACs have some output capacitance, and that's output capacitance right at the summing junction. And capacitance at the summing junction implies a lag in the ability of the loop to move, which means it's going to have to be compensated by a lead in the feedback loop. So whenever you're trying to get a DAC to settle best, you're going to need some capacitance in the feedback loop to cancel the inherent output capacitance of the DAC. Bipolar DACs are pretty friendly in that regard. Their output capacitance is relatively small and, very important, pretty much constant with code. It's just a bunch of collectors hanging off the output node. What that means is a single capacitor will provide optimum compensation for all codes. MOS DACs, that's not true. The output capacitance is significantly larger and changes significantly with code. It can change by an order of magnitude, which means generally the best you can do for an MOS DAC is pick the worst case settling, which is, I think if I remember right, all bits off, all bits on, and comp for that, and take what you get for everything else. So the point is, if you pick the wrong comp cap, in this case, this is the command pulse to the DAC. This is the large signal slew of the DAC. and that is the settling waveform down there. So this is 10 millivolts per division on top of all this. That's the case with no feedback capacitor, and now you've just got pure capacitance at the summing junction, and it rings like a bell. If I get a little too enthusiastic, I get a classic overdamp response, which is safe. It's just the plane will crash slowly rather than quickly. Okay? Somewhere in the middle, I'm going to get pretty much a critically damped response, and that's what I'm after. The plane will land and you can get off at Kennedy. Got to help you in New York City. Okay. This is Appendix C in the handout, and what this is it's really a tutorial on loop stability. And we're going to go through and talk about loop stability. The centerpiece of the tutorial is putting things in the feedback loop of op amps, and all these circuits should be familiar. We've covered them in the previous 2 lectures, but I haven't talked a great deal about why they are stable and how we got them there. So the next 12 or 15 slides are putting things in feedback loops of fast amplifiers, getting them to be stable, and when they're not stable, knowing what to do. You know, that typically comes under the heading of Bode analysis, but I'm going to promise you we're not going to mention poles, zeros, Bode plots, loop stability analysis, or anything else. We're going to do it in English. Let's take a look at this figure, which is drawn from the text. It's basically a 50 megahertz op amp with a power booster. This is the 200 mil stage we played with. Typically, when people do things like this, the phone call you get is, it oscillates. Okay? There are questions to ask when the customer says it oscillates. Remember, I said there were 2 kinds of oscillations in a situation like this. One is something within the booster is oscillating. That is to say, it's not a feedback loop phenomenon. There's something in here oscillating. And I said emitter followers can oscillate, particularly emitter followers driven from low impedance sources. This is a typical emitter follower oscillator down here. So what we're going to do is we're going to take this circuit in the text that moved well, and we're going to begin our study of loop stability by messing it up. Let's take out the ferrite beads and see what happens. It buzzes. Okay, this is typically not a loop issue. When you see something like this on an oscilloscope, before you say, it doesn't work, it oscillates, say like this, at what frequency does it oscillate? That's the giveaway. The magic is that typical follower and device level oscillations are fast. The horizontal scale got cut off here, but my recollection is it's in the microsecond range. So what that says is this stuff is in the tens of megahertz range. The first thing you want to know in a circuit like this is it a loop oscillation or is it local, device level? Presumably the op amp was debugged prior to sale for oscillation problems. When you see real fast stuff like this, tens of megahertz, the likelihood is it's device level stuff. Now what about loop stuff? Let's take a look at why loops oscillate at all with no mathematics. If I take a slow amplifier, in this case this is a 1 megahertz device here, so that's a 741 class kind of speed, and this is about a medium speed 20 megahertz kind of integrated power booster here. Your stomach tells you the following. This thing essentially looks transparent with regards to delay. This is very slow. You can inherently model this, if you will, as already having a big capacitor from summing point to output. It's a 1 megahertz kind of thing, and it's instructing a 20 megahertz kind of thing to close the loop. In the pit of your stomach, you know when this moves its output, the phase, the delay, if you will, through the loop, looks like nothing as far as this is concerned as a 1 megahertz device. And that's exactly what you get. You get basically a single lag response. Loop stability is free, if you will, when the op amp is much slower than the booster. Input pulse, this is pure slew. Where's the delay in this circuit that sets the slew? The delay is the slow bandwidth. that amplifier. The loop stability is free, it can't oscillate. The 20 megahertz booster looks infinitely fast. Now let's make a change. Instead of a 1 megahertz amplifier in our simple circuit, let's put a 100 megahertz amplifier there, driving a 20 megahertz booster. Now we got a very different situation. The brains in the circuit is much faster than the muscle. So movement here is significantly phase delayed from getting around the loop relative to 100 megahertz of bandwidth available here. Put the same pulse in, it screams. The other thing you'll notice is, look at the frequency. That's the first question to ask. Look at the frequency of the screaming. Because what that tells you is, this thing is a phase shift oscillator. You're measuring the phase shift in the loop. That gives you a clue to how close to the edge of stability you are. You always want to ask, what's the frequency? And you notice with the loop oscillation, we're not anywhere near tens of megahertz here that we are with device level oscillations. It takes some time for that signal to be transmitted around the loop. So in this case, loop oscillation is free when the op amp is faster than the booster. Now, let's go from silliness to suicide. Let's hang on to our 100 megahertz amplifier and put a booster in the loop, which is a little slower. What's going to happen? You notice no comp cap here, so this thing's wide open. This thing looks like phase shift through here, and if this guy is faster than this guy, ain't gonna work. You still got too much phase, but you notice something? That's a 20 megahertz integrated buffer. Look at the frequency of oscillation. Maybe 10, 12 megahertz, if that. This is a discrete buffer. It's faster, take it from me, significantly faster, but not fast enough. But you notice something? The frequency of oscillation is much faster. Why is it faster? Because the delay time through that is significantly quicker than the delay time through the former buffer. What that means is almost, but not quite. But the real relevant information is not that the circuit oscillates, it's that it oscillates at a much faster frequency. It means you're almost able to close the loop here. And in fact, the way you would close the loop, if you remember the text circuit, at about 3 or 4 puff right across here, you cool this off as much as you have to get enough lead back to the summing junction, basically around the lag of this stage to make the thing stable, and you don't cool it off any more than you have to, because then you start giving up speed to do that. And you notice again, in accordance with the preaching I did in the first lecture, I don't use a feedback capacitor to stop the thing from oscillating. I stop it from oscillating by killing the gain bandwidth in the circuit. I might use a feedback cap here to trim overshoot, but I want to kill the gain bandwidth. There is where the cap should go. Now, if the 200 milliamp booster didn't work, you remember this one, the 1 amp booster? That clearly isn't going to work. It was slower in the text examples. But let's throw it in anyway and see what happens. So this is the 1 amp circuit we looked at before, which was slower. You notice the oscillations are larger in amplitude and lower in frequency, reflecting the circuit's, the booster's slower bandwidth. The other thing you'll notice is, remember I said when I described this circuit, you had asymmetric bandwidth in this thing, gain bandwidth. You've got just current gain through here, followers. You've got voltage gain with this fast quasi-connection here. You notice that the amplitude and frequency of oscillation are different for positive and negative sides. That reflects the fact that you've got asymmetric gain bandwidth in this thing with this quasi down here. So these waveforms, as ugly as they are providing you very valuable clues to how to shut these things up. And if you remember the text circuit, the fix was the same here. Kill the gain bandwidth there. Perhaps a less expensive way to kill the gain bandwidth than adding a cap is to specify a slightly slower amplifier. then the cap is, quote, free, unquote. Okay, now, let's put the beads back in. This is the circuit we started our study with. And that's exactly what it looked like before, and that's what it should look like now. Let's take another look at stuff in the feedback loop and what it does. Remember this circuit? This is the one I like so much. It's a simple current source. You've got a diff amp running at a gain of 10, looking across R, feeding back to the negative terminal. The current, excuse me, through the grounded load is I equals E in over R times 10. Lovely and simple. So you've got a voltage-controlled bipolar ground-referred current source. What do these RC components do here? Well, when in doubt, take them out. Let's take the cap out. No. First, let's take a look at it with the components in place. It looks like it did in the text. It's fast and clean. No residues, except for William's lousy termination job. Remember I moaned about bad terminations on the pulse generator? There I am, cheaping out. Now let's take them out. If you take them out, what happens? You've got phase-shifted feedback here. The only AC feedback path now, with this capacitor removed, is the delay path through this amplifier. That's called a phase shift oscillator if this guy is significantly fast compared to that. And sure enough, that's what happens. Now, remember this circuit? This is the same circuit with the high power 1 amp booster stage in here. So now we're really going to commit suicide. We're going to take the cap out like we did in the last example. We're going to have the phase of the diff amp in there, the lag of that, and the lag of the booster stage. Okay? So it's fine. We missed it. There's a picture missing here. This thing screams like a banshee with this capacitor out here. We're missing the picture. It's got to. If it screamed with the cap out here with just this delay, it's certainly going to get into trouble with both of these things in the loop, unless we kill the gain bandwidth locally. With the cap in, it's happy. The picture you want to see, I ain't got. That's the end of this tray. Figure out how to get out. I mentioned a couple times during the lectures that I have this wonderful magic pulse generator that generates this super fast rise and fall time where I can walk up to a circuit, I said, and I can stick in just this hellaciously fast edge and look at the response of the system to what is essentially an infinitely fast edge. That's an extremely useful piece of test gear for testing circuits and test setups, scope, probe, end-to-end bandwidth stuff. Now I'm going to show you how it works. The way I do this is I avalanche transistors. The magic in this circuit is right here. All this is, I'm not going to spend much time on this, it's an integrated circuit switching regulator that'll run off 1.5 volts. You can see the outlines of a flyback here. The switch pin closes to ground periodically, generates high voltage flyback events, runs through this voltage doubler, and we end up with about 90 volts here. So all this junk is just a convenient mechanism to generate high voltage from a AA battery. The magic is right here. I used to do this function with tunnel diodes, but they've become insanely expensive, and the pulse isn't as big. The way an avalancher works, you start out with high voltage here, much higher than this transistor is designed to handle. 90 volts through a megohm charges this 2-puff capacitor. At some point, the collector potential is too great for this transistor to handle, and it avalanches. You dump C through the broken down collector-emitter junction. And what do you get out of this thing? It happens. Avalanche mode is fast. Bang! What you get out of this thing, 2-puff dumping through essentially a dead short in the transistor into 50 ohms, gives you, measured on a sampling scope with a gigahertz of bandwidth, gives you a 10-volt high pulse with about 200, 400, 600, 800, about a nanosecond of base and 350 picoseconds rise. It's just a wonderful, cheap, fast edge. Of course, I stole the basic technique. This is pretty much the technique, a stripped-down version of the technique that Tektronix used in the 60s to generate the gate pulses for sampling bridges. Because when you build a sampling scope, the name of the game is, just like with a strobe light, how narrow a window can you look through as you take your samples. So there was all this science and art that went into developing gate pulse generators to get that bridge on and off with incredibly narrow windows. And this is essentially a chopped down version of this. If you're interested, I've also got a version of this, which if the art gets done, you'll see 6 or 7 lectures down the road where I can trigger this. I mean, right now, this thing's basically just a free-running RC oscillator. You charge through R, C dumps, and you charge some more. This thing's just a relaxation oscillator. I've got a version of it now that you can trigger, which if I don't get into slide form, if somebody wants it, I can give it to you now.
Question. Clearly, if theirs is sampling yours, they've got one that's running a lot faster. Maybe that's not clear, but is it true that theirs is running an order of magnitude faster?
This is the perfect question for this slide, because I've been setting you people up throughout the last 2 lectures. Remember, I've been harping on the fact, the perfect question, this guy gets A, but he's a prof, so it doesn't, he's a worthless A. I've been setting you up. Remember, in various circuits and for various waveforms, I tell you, you know, when you see rounding and symmetry in waveforms at speed, it's not necessarily the case, but it's likely that something's bandwidth limiting. Look at that waveform. You know, I'm beating my chest that this is taken on a 1 gigahertz sampling scope. But never mind the number. Williams says, when things look too symmetrical and too clean at speed, the thing may be bandwidth limiting. Well, the problem is 1 gigahertz is the fastest oscilloscope I've got in my house. Okay? So what does the thing really look like? And to get the answer, we have to go to God's own oscilloscope. Okay, so one Sunday afternoon, I went into HP on the Hill, a fire-breathing, nitrogen-cooled monster oscilloscope. Okay, and in a 10 gigahertz bandpass, what you see is when you see edges that look symmetrical at speed, something may be bandwidth limiting, and it is. Kovacs is right. A gigahertz is not enough bandpass to see what's really happening. At 10 gigahertz, if I remember right, the rise times come out about 230 nanoseconds versus an observed. You notice what the rise time is here? The rise time is 350 picoseconds on that scope. If you go through the numbers, 350 picosecond rise time is 1 gigahertz. We're looking at the scope. It's tilted over. At 10 gigahertz, the rise time is 35 picoseconds. So this feels pretty good. What it really looks like is about 230 on the rise. It's going to be a while before instruments like this show up at the flea market at Foothill College. I'll buy one. The point is, it's extremely valuable, especially when it costs nothing, to have a pulse generator around like this, because you can stick essentially infinitely fast steps into fast test setups and verify the integrity of your measurement setup. This is what the sampler head, or what the avalanche head looks like. There's the transistor right there. The high volt, the 90 volts DC comes in here. Here's the 2-puff cap. And why am I using 2 1-puff caps instead of a 2-puff cap? For a couple of reasons. One was, you've got to tweak this thing. Every one of these transistors is different. So you start out with a puff and you walk up, okay, to get the results you want. So you can see, within the limits of discrete technology, I've mashed this up as close as I can. Practically speaking, BNC connectors really start running out of gas at these frequencies. The real way to do this is a type N type connector, or the beautiful old General Radio hermaphroditic things, which are probably the best connectors ever built at frequency. It's just GR and Tech were the only guys who ever used them, and Tech gave up on them because everybody wanted to go BNC. But in fact, I think the Avalancher may be running faster. You've just got too much parasitic here. That's what the thing looks like when you're done. It's just an old busted probe piece with the actual avalanche head, and in here there's a 1.5 volt regulator and the 90-volt switcher. That's it. So you can walk up to the circuit anywhere, BNC your way in, and stick this edge in and say, what is my probe circuit test measurement setup doing with this edge? How much can I believe? Okay, this is the funnest section of the whole lecture set. I showed you lots of neat and pretty schematic diagrams, okay, and very pretty scope photos. And I also made some comments about breadboarding. And I said early in the first lecture, and I gave you that 3-slide set of breadboards, I said people waste an incredible amount of time because they're spooked by high-speed circuits. They think the breadboards have to be absolutely gorgeous to work. And I went to some pains to say the breadboards do have to be gorgeous to work. But in a well-designed circuit, they only have to be gorgeous in a few spots. If you treat the highlights of the circuit correctly in terms of layout, you can save hours, sometimes even days, in the construction of the breadboard. You identify the circuit nodes where you've got problems. You treat those nodes very carefully, and everything else, you don't waste any more time than you have to get the breadboard up and running. This circuit technique is not recommended at speed. Don't do this. Okay? If I had my way, all the L sockets ever built would be in the bay. They're terrible. Okay? We get stuff like this in the mail. Don't do that. Yes, people do try and wire wrap 100 megahertz 12-bit circuits. Don't do that. This is a customer I spent 3 phone calls and a half a dozen faxes with, and when this arrived in the box, I almost fainted. Yes, people do that. They don't understand why it won't work. Now let's get a little more serious. In the opening lecture, I talked about probe-related problems. One of my favorite ways of getting rid of probe-related problems is to get rid of the probe. When the circuit impedances make sense, that is to say, the circuit is willing to drive the input of the scope directly, and usually at high speeds, that means the scope input capacitance, not resistance, is usually not a problem. When you can get away with it with regards to that, and you're really going like crazy, get rid of the probe. Just bolt the breadboard right to the scope. That's one of the reasons I like old scopes. They're heavy. You can bolt big breadboards to them. Okay, let's take a look at this close-up view of a prototype of the avalanche pulse generator. We're talking about something that makes waveforms in hundreds of picoseconds. Look at this breadboard. Okay, see here? That's the DC to DC converter. I'm not going to waste 5 minutes breadboarding that. It's a waste of time. What you can probably see better in the handout is the attention that went into the layout in the business end of this thing, which is the avalancher. This can be ugly. But this here, that's got to be bulletproof, and that's where you spend the time. Similarly, look at the settling time test fixture. Okay, this is a tough measurement. You can't play games here, except where you can. Here's the DAC. This is a sampling scope probe right here. This stuff down here is my sampling front-end diode bridge that I made. Let's look at a couple of things here. I'm trying to measure 12 bits settling in a couple hundred nanoseconds to a millivolt or less. You notice what I did here? Here's all the digital stuff driving the DAC. See the copper-clad stripe? I broke up the ground plane completely. I don't want any of these digitally circulating currents mixing into this analog stuff here. I pipe the grounding back directly from the digital end. Okay, I don't even want the circulating. I don't trust the ground plane as fat as it is at these speeds and these resolutions. That's what that stripe is right there. I just tore the copper off it. Second, my sampling bridge that I built and the switch drive and everything else, that's built on a separate board which is grounded back at the power plane. I don't want the DAC currents and the bridge currents mixing either. Built on a separate board, clad's not soldered here for common ground. I do the grounding at the point of measurement. Also, you'll notice, remember I talked about pulse generator and the 50 ohm termination. There's the 50 ohm pulse generator termination. I don't do the termination on the board. I don't dump a 5 volt pulse generator into 50 ohms and get 100 milliamps of ground current flowing around in here. I do the termination coaxially so that this ground pulse generator current flows through the cable, through the terminator, and back to the pulse generator. I never dump those currents into my ground system here. By the way, this sampling probe here for the 661 sampling scope, every university EE graduate should be required to use that probe. It makes you feel like a real engineer. That is a cathode follower probe at 900 megahertz. It gets hot, okay? It's big, it's ugly, it's a Frankenstein thing. You feel like a real engineer when you use that probe.
Question on that.
Yeah,
Where do
question?
you tie your analog and digital ground together?
The question is, where did I tie the analog and digital ground together? Good question. Here's the 5 volt stuff here. Here's the plus minus 15. The grounds are tied together back here on the wall at the power supplies. That's where I tie them together, at the supplies. In theory, when you tie analog and digital ground together, you should have almost no current flowing in that reference connection. If you do, something's wrong. Because that's what you're doing. You're referencing the supplies to 0. There should be no current flowing in that point. If there is, you've got a ground loop. Okay, remember the circuit that I thought wouldn't work but did? The gain of 1,000 diff amp with 40 megahertz of bandwidth? Here's the breadboard that produced those pretty waveforms. See all this junk up here in the air? That's the low frequency side of that servo. Remember, it was a parallel path kind of arrangement. I ran all the fast AC stuff through one path, and then ran all the DC and low frequency stuff through another path. So you can see the DC path, I've got sockets here, I've got space wired stuff, the fastest way to wire this possible. The AC path is kind of hard to see. It's all snugged up against the input here. Okay, it's just bolted right down to the breadboard. The reason I like to space wire the slow stuff is I can reserve the good spots on the ground plane where I need them for the real fast stuff and spider wire the DC stuff around it. I could wire the DC stuff back in here if I wanted to, but in my case it just takes too much time. There's no point. The other thing you'll notice I'm doing is this is a gain of 1,000 amplifier, so I've got to generate an input pulse of millivolts to drive this thing. I could just take lots of attenuation out of the pulse generator, which is what I'm doing here with a stacked attenuator set, and believe that the pulse of millivolts here must be as clean as the pulse of volts here from the pulse generator, if I believe that my attenuators are that good. But if I'm wise, I'll verify the integrity of what I put into this amplifier with a true differential FET probe. Why do I use a differential probe? Because in millivolts of input, I don't trust my ground integrity. I want to look differentially. So if Tektronix did their job and the output of the pulse generator looks good, my millivolt level pulse down here should look good. But I want to know it. I want to see it. So I verified, and I verified differentially because I think the ground integrity is good, but I don't know for sure. Same breadboard. This is a tighter look at what's going on here. Here's the DC stuff again. Here's the stacked attenuator section. The differential FET probe verifying the millivolts level of pulse here. What's this? Remember I talked about in the first lecture, it didn't take much stray capacitance across an input resistor to get you into trouble. That's a piece of copper clad right there. I'm worried about spray off the end of the attenuator here, leaping into the high frequency stuff. That's a shield. If I've got anything spraying off the end of this attenuator, any RF movement off of that thing, this will take it out. That's what that is. It's a piece of copper clad soldered across to stay out of trouble. In production, that's expensive. All of these breadboards presuppose that the object, when you breadboard, is to make the circuit work. To build this thing in production, you're going to have to do some thinking about layout. No floor manager wants to hear about shields like this. What you want to do is build the circuit so it works, and then start cutting stuff like this out to see what relative degrees of sensitivity to layout you've got. Battleship the thing first, then start cutting it apart to see where the sensitivities lie.
You don't worry about inductive coupling?
Question, I'm not worried about inductive coupling where?
Well, you've got current loops there. I mean, the attenuator current has to be flowing somewhere in the track.
The attenuator current is flowing into the attenuator and right back through its coax out.
But that is loop current there.
That's a loop, but if the attenuator guys have done their job and this thing is truly coaxial, it should be okay. That's why I never, don't even think about trying to build your own terminators or attenuators. You know, you can't do what they can do. This is the fast photo integrator. Remember that thing? You get the integral of the photo pulse coming in. In this case, I'm early in the breadboard development, I'm simulating the fiber optic input with a pulse generator and a resistor. Look at all the shielding here. If I remember right, that had a 10 puff input capacitance. So I'm paranoid about stuff coming in off the end of this terminator getting into the summing point. Here's another look at the same thing. You can see lots of shielding of the summing point. I'm just terrified of anything. A 1/10 of a puff coupling from here into the high speed stuff is going to kill me with a 10 puff integrating cap. Now we've got the thing set up. This is the adaptive fiber optic trigger. So here's the fiber optic input here. Here's the fake input. In other words, the real photo current comes through here, this fiber, but I can fake it with a pulse generator. What's this here? The other thing is, before we go to that, remember that thing had an adaptive trigger, which was pretty much slow? That's all spider wired here. This stuff's up in the air. Okay, the fast stuff is clustered around the input connectors. But what's this? Here's the pulse generator input to simulate the fiber input, which is this, which came later. See the resistor going through the hole from the output of the pulse generator input? And then there's another resistor, and then another resistor, and then finally I go into the amplifier. Why don't I just use one resistor here? You know, the shield in the hole, that kind of makes sense. Williams is trying to shield the end of the BNC from getting into the summing point here. But why 3 resistors? Because the shunt capacitance of the resistors is now distributed across 3 resistors instead of 1. So what I'm trying to do here is break up any RF transmission from the input of this thing into the summing point with shielding, and then whatever shunt capacitance there is across these resistors, I'm going to divide it away times the number of resistors. Is there a penalty there? Yeah, there's a penalty, which is to say, when you go from one resistor to the next, any capacitance from that point to ground looks like a lag. So at some point, the technique falls apart. This is the 1 amp output stage, okay, with the quasi-complementary bottom end in this thing. Here's the input. Here's the control amp right up near the input. I'm keeping my inputs as tightly wired as I can. Now the output stage doesn't really have to be that tightly wired, and why is that? Because it's a 1 amp stage and it operates at fairly low impedances. So whatever shunt capacitances there are don't have as much effect as you might think because there's lots of current flowing. Notice that bypassing the power transistors are here and here, bolted into the copper clad. You notice the bypassing? Lots of microfarads of tantalum helped by ceramic right at the point of load, the power transistors, right there. This is the, what is this thing? This is the 20 megahertz sine wave crystal oscillator. This is where we got rid of the light bulb and replaced it with 15 electronic components. There's the crystal. Okay, the actual oscillator is buried down in here. Okay, The AGC stuff, this is pretty tightly wired in here. Okay, because I am worried about strays at 20 megahertz. But the AGC, that's pretty much low frequency and DC stuff. I can get away with garbage there. No sense wasting time. Here is the Varactor tuned wing bridge version of this thing. This thing here, I elected to build on 2 breadboards. This is the AGC. You notice there's not even a ground plane here. And the reason is the AGC is slow. It's basically DC to 10 or 20 hertz AGC kind of action. I didn't waste time with a ground plane. I tacked the ground strip on this breadboard to the copper clad on the fast guy now, and all the wideband stuff is tight around the output connector. But I can bring in the DC signals. There's a resistor here. So this side of the resistor, this is the AGC output here. This side of the resistor, that may be crucial in terms of speed. So I'll keep my lead length long on that side of the resistor, and the inputs are done the same way. Remember the monstrously complicated 10 megahertz V to F converter? This is an example where there was enough tough about this circuit that I had to spend some time on this breadboard. A couple of things about the breadboard and the probing technique worth looking at. Here's the charge dispensing loop in that V to F. It's so tightly wired here, it's almost impossible to see in this picture, but you'll see it in the next picture. Remember it had a DC stabilization loop, chopper amplifier? I can mount that in a socket. Look how long the lead lengths get out here in the DC section. But things get tight again in the switched voltage reference section up in here, because this does have to move at some speed. You also notice the probes, there's no ground straps. I've got tip adapters here. You can really see it now in this picture. This is expanded. Here's the DC servo amp asleep out here through long lead lengths. But the AC stuff, all the summing junction and stuff, is just buried. The lead lengths here are as small as I can make them. You can really see now the tip adapters to keep the ringing down at the point of measurement. The other thing is the output of the integrator in that circuit drove a comparator. I can make that lead length relatively long, even though it's going to move at 10 megahertz. Why? Because the output of the integrator is at relatively low impedance. I can get away with that. The time to height converter. This was a circuit that measured, I think, a 250 nanosecond pulse to a couple of nanoseconds. Okay, same kind of stuff. Okay, this is the current source in here for generating the ramp. The polystyrene cap is right over there. So this PNP transistor is trying to make a ramp into that cap. This is the turn-off transistor and all its attendant speed-up stuff, if you remember that. This is the one-shot to set up the timing. That's far less critical, and you can see the wiring in here takes a holiday. The automatic trigger, okay? Same sort of stuff. This is, remember, a derivative of the photo automatic trigger. The wideband sections of this thing are clustered around the input, and they're tight. As I get off into the adaptive sections, which are pretty much slow, remember we charge up caps and set trigger points for the comparator? We can just breathe out in here. There is no point burning your fingers soldering tight in here when this stuff is relatively slow. The output comparator is fast, however. I can route the DC lines fairly crudely, but notice the output is the AC wire to this thing. The signal of the output comparator is one of these long ones here. Why can I get away with that? Because I'm driving out a low impedance from the op amp, so I can get away with that. But you notice I route that high-speed stuff away from the DC decision-making stuff. I don't want the spray from that line getting into here and messing up my adaptive trigger. So I run it around the clover leaf to the comparator. This is the RF leveling loop. This is the one where I borrowed the analog devices part and used it. This kind of breadboard has all the earmarks and is in fact an iterative procedure. You can see there's 3 basic circuits here. Okay. This is the actual RMS to DC converter, which got built to this point. So you say, fine, that function of this thing works. This was the, what is this thing here? The RF, that's right, this is the RF preamp to drive this thing. Okay, and finally the multiplier here to close the AGC loop. Then you tack all the copper-clad boards together to maintain low impedance in the grounding network, and hopefully the whole thing's going to work. So I checked out each one of the three functions first and tacked them all together. The other thing you'll notice, yeah, when you're trying to measure something like this at the speeds this thing was running at, this is reversed. This is RMS to DC, so the scope doesn't have to look very fancy, but the generator generates the RMS test signal. I don't trust cable effects when I'm trying to measure something like this. So this is AC going in, terminated right at the generator, and I bolt the breadboard right to the generator. I trust the flatness of the generator. I don't want to have to worry about 3 or 4 feet of cable plus terminator. I just bolt the breadboard right to the generator. This is the voltage programmable current source. That's the diff amp looking across the resistor with the servo amp. Same sort of stuff. Here's the voltage command input to set the current. Again, I'm terribly worried about spray coming off my input connector, getting into this amplifier, the control amplifier, so I've got a shield here. This thing's in the feedback loop and operating across a relatively low impedance shunt. That's the diff amp, so the wiring can get a little looser in here. It does. For lazy people, our company makes available stuff like this. This is very appealing because it's pretty and it's nicely set up. The problem is, of course, it's ossified. It's hard to make changes. And what breadboards are about is making changes. You have, if you will, convergence problems with a breadboard like this. Okay, one other topic I'd like to cover. We're almost done here. Does anybody in this room recognize this diagram? This diagram is from a Stanford University thesis in the 30s by Hewlett. This is Hewlett's original diagram and his thesis. Why am I showing you this? The reason I'm showing you this is there's lots of ranting and raving in the marketplace today and in the IEEE conferences and magazines about the latest and greatest technique for high-speed stuff, which is current mode feedback. The problem is the technique is old. Bill Hewlett used it. In fact, current mode feedback predates so-called feedback or voltage mode feedback because people couldn't do voltage mode feedback until there were op amps. And there wasn't op amps till there was basically George Philbrick, who made 2 high impedance inputs. Current mode feedback, which RF guys for years called cathode feedback, okay, has been around as long as feedback's been around. It's on Nyquist's original patent. So before you believe all the marketing hype and all the stuff in the red rag about all these new techniques, let's go see how new they are. This is Hewlett's original circuit in his thesis. There's the Wien bridge. There's the lamp. So this is very similar. The elements here are very similar, and in the next lecture, next week, we're going to talk about this in depth. But the elements here are very, very similar to the 10 megahertz circuit we showed with a light bulb. So this is Meacham's contribution, the lamp from Bell Labs. This is Wien's contribution. Yeah, there was a Wien. His name was Max Wien, and he did that bridge in 1891. But he wasn't making oscillators. He didn't have any gain. He couldn't make anything oscillate if he wanted to. He was measuring R's and C's for telephone work. But the point is, let's look at Hewlett's oscillator. If that's the Wien bridge, we know that's got to be positive feedback. There's the output here. So positive feedback through the bridge is to the first grid. The gain stabilizing feedback, where's that? Well, here's the lamp right there. The gain stabilizing feedback is also from the output back to where? The cathode. That's feedback to a low impedance node. That's current mode feedback. So Hewlett beat all the guys in the red rag by at least 50 years. Let's get a little more modern. This particular diagram has a special significance. Here's a FET. Here's a 2-transistor gain stage. Here's the feedback right here. This is a FET probe from Hewlett-Packard, about 60s. Here's the collector, comes out right there. There's the feedback node. That resistor and that resistor set the gain of this stage. This is just a follower out to drive the cable up to the scope. That's feedback to a low impedance node. That's current mode feedback, circa 1965. Why is that significant? That circuit was done in Loveland, Colorado, I think by a guy by the name of Dave Nelson, who's a good guy, who founded Comlinear Corporation, which built the first commercial, the so-called first commercial current mode feedback amplifiers. Well, not quite. Dave was building FET probes in the 60s. He knows better. What their contribution was they civilized this thing. They made this point available to the user at the output. They called that point the negative input. They called that the positive input, and they had a company. 1965, Hewlett-Packard. This is the input amplifier. Actually, not quite the input amplifier. It's the main video amplifier for a thermal RMS voltmeter, 3400A. So we got about 40 megahertz of bandwidth here, stacked up stages. This is an interesting amplifier to study because about every trick known to humanity to get flat bandwidth within 1% to 10 megahertz is available in this stage. I mean, lots of stuff going on here, okay, to make transistors that could not and should not be able to do this. But the point is, here's the output fed back to an emitter. That's feedback, so the gain is set by these impedances and that. That's feedback to a low impedance node. That's current mode feedback. Tektronix, 1964, 453. Now here's a circuit I would love to see somebody try and take apart and splice. This is hard to deal with. In 1964, there were no FETs worthy of instrumentation grade problems. You still had to use fast Nuvistor triodes for the inputs of scopes. This is a Nuvistor triode follower, current source loaded here. The biasing on the current source sink here is set up to temperature compensate the grid cathode temperature characteristic of this. I'd like to see a splice analysis of this circuit over temperature. But see this configuration here? 2 transistor gain stage. The feedback here is through here, through this attenuator. But there's the summing point in the circuit. That is the negative input, if you will. That's feedback to an emitter, which is a low impedance point. That's current mode feedback. One last example, Tektronix P6042 current probe, again, mid-60s, predating all the hullabaloo by at least 25 years. Here's the output of this thing through this impedance right to here. That point right there, this impedance and that impedance set the gain of this RF stage. That's feedback to an emitter. That's current mode feedback. They didn't know that then. They just called it feedback. And finally, a couple of loose ends before we break. Remember the radio station application in the first lecture? Make sure you fill out your FCC Form 401 before you build that circuit. President Clinton will come get you. And if you decide to make money at it, here's the form you'll need: application for AM broadcasting station. Okay, I can take questions. That's the end of the high-speed stuff. Wow, that's the shortest lecture we've had.
Do you ever worry about magnetic coupling and things like that?
The question is, do I ever worry about magnetic coupling? And the answer is yes. Okay, if you've got breadboards or circuits where you've got lots of current flowing somewhere, and you also got stuff on the breadboard operating at low currents or microvolts, you really want to look at just the same way as you consider the disposition of currents flowing in the ground plane, which is what current in the plane is flowing through what other current. You look at, if I'm generating fields, where are they going? What's the disposition of those fields? instrument people constantly have to worry about, I've got a power transformer here. Which way do I orient the magnetic component so the field does the least harm? You know, it wouldn't be wise to put a switching regulator transformer right next to a microvolt front end, for instance. Sometimes you have no choice. Boxes are getting very small now, and you have to do that. So you start thinking about, how do I shape the transformer for minimum damage? Because you'll do everything you can. You know, the simple-minded way to deal with magnetic fields is lots of mu metal. That's expensive. Okay? The better way to do it is to think about it on the front end of the layout. Yeah, when you've got high currents flowing, magnetic components, or both, you have to think about where are the fields going and what are they affecting. Anything else?
Well, thanks very much, Jim, again, and we look forward to the next one.
Okay, there's a chance I may be called out of town this week. And I may or may not be able to make it next Friday, but I'll let Greg know as early as Monday.
Sure, we'll just do a logical shift left.
So we'll just do a shift left, okay? No, we'll charge the cap to a different building.
I also wanted to hold up so people could see that this is what these lectures are keyed to, because
They're probably gonna want the book.
Yeah.
Some of the slides aren't so good.
when we make the VHS tapes, we'll have to ship them with these.
Okay, I think I'm about 80% certain for next week, but if you're planning on coming, give Greg a call.
Yeah.
Okay, and next week we're gonna slow down several decades in frequency. Thanks very much.
Thank you, Jim.